Hello everyone, my name is Brett Psyche, and today I'll be presenting our work on combining precision tuning and rewriting. So when writing numerical code, there are two things we try to minimize, error and latency. In certain scenarios, we want to minimize latency over error. In others, error over latency. And of course, there are other scenarios where we want something in between. So for any expression or function, we have a Pareto frontier of possible implementations. And the key is no one trade-off is right for every application. That is, we need to explore the Pareto frontier depending on the scenario. And we generally use two techniques for this, precision tuning and rewriting. In general, precision tuning increases speed by lowering the bit width of the representation, while rewriting increases accuracy by avoiding things like cancellation. Now, it's difficult to tell where we should apply these techniques. And in recent years, there have been numerous tools made to automatically apply precision tuning or rewriting. Now, if you have an expression, just by looking at it, it's hard to know which of these techniques you should choose. And you may want to use both. So in the past, you take a precision tuning tool, take a rewriting tool, and use them together in some manner. But this raises some issues. What order should you use them in? How many times should you run them? And it's hard to share data between runs. So the obvious solution is to use precision tuning and rewriting within the same tool. And what we found is by combining precision tuning and rewriting together, this allows you to produce a rich set of Pareto optimal accuracy versus speed trade-offs. In addition, we found that finer grained interleavings of the two techniques create better Pareto frontiers. Precision tuning can be a rewriting problem, and local error analysis helps guide both of these techniques. So we took these insights and we made a new tool called Pareto Herbie, or Furby for short, that takes an input expression, automatically and simultaneously applies precision tuning and rewriting, and outputs a set of Pareto optimal implementations. So before I talk about Furby, I'm going to talk about the tool is built from, Herbie, so that we understand some key concepts. Herbie is a rewriting only tool that improves the accuracy of floating point expressions. In a nutshell, it takes an input expression P, samples points in the input domain for evaluation, generates candidates within this improved loop, and produces a better expression P prime through a phase that we call regimes. So more in depth on some of these phases, localize will take an expression from the candidate table and identify which operators have high error using something called local error analysis. What this does is for every operator, you take the exact values of the children, compute the approximate and exact result at that operator, and then compare the two. And that usually gives you a good idea of which operators are problematic. In addition, this prevents the error of the children from affecting the error of the parent. Once Herbie knows where to rewrite, it'll use a database of hundreds of rewrite rules to find and replace sub-expressions to produce new candidates. There are some other phases that I won't mention. And then pruning will only keep the candidates that are of interest based on some criteria and add them to the table. Once the improved loop is run multiple times, we extract the regimes. And what this does is, imagine you have a candidate with this error profile in red and another candidate with this error profile in purple. Regimes will combine these candidates with a branch condition to produce a new expression that is better than any of the candidates on their own. So that's kind of Herbie at a high level. And we can think of Furby as really just an extension of Herbie, that by adding precision tuning and that outputs multiple expressions. So we made changes to these phases here in blue. And the first one I'm going to talk about is rewriting. So this is a example of a rewrite from Herbie. And the key is Herbie only has a single global precision. That is, if the user specifies double, all these operators produce double precision results. But in Furby, we want multi-precision expressions. So we specify each operator to particular precision. And this allows us to match expressions based on both operator and type. Now we can introduce a new class of rewrites here called precision rewrites that change the precision of an expression. And these two classes of rewrites implement rewriting and precision tuning within Furby. Now, where should we apply these precision rewrites? Herbie rewrites at places of high local error to improve accuracy. So we should use that same idea. We should increase precision at places of high local error to improve accuracy and decrease precision at places of low local error to improve speed. So the next phase that was changed is pruning. Now, once again, pruning takes the candidates that were generated in the improved loop and only adds to the candidate table the ones that are of interest based on some criteria. Within Herbie, that criteria is a candidate must be more accurate than every other expression on at least one sampled point. Now this won't work in Furby because the table will become biased towards slower, more accurate expressions. So things like 1 or 2 term polynomials generally will not make it into the table. So to fix this, we add this second condition that we only compare against other expressions that are at or below the cost of the candidate. That is, a candidate must be best in class on at least one sampled point. Now, what is this cost I mentioned? Well, it's just a measure of the latency of the expression. Now, what we found is trying to get precise timing data for each candidate is not practical because we need to evaluate it many times. And within a single iteration, Furby may produce thousands of candidates. And what we found is we only really need a relative speed comparison. So we should just use a simple cost model to estimate the speed of expressions. Now here is kind of the default cost model from Furby, just as an example. For every operator, we give it a cost. Arithmetic operators have a low number, library functions have a large number. And we multiply the operator cost by the bit width of the representation. That is, an add in double is twice as expensive as an add in single. And to calculate the cost of expression, we just go through the AST and add up all the operator costs, of course, keeping track of or respecting conditionals. Now, of course, better cost models exist. Furby is modular, so if a user has a better cost model, they can swap theirs out for the default one. The final phase we changed was regimes. For regimes, we want to extract multiple expressions rather than one. So we iteratively use Herbie's regimes algorithm on the candidate table. Now, at a high level, we have a cost bound that is initially higher than all the candidates higher than any of the costs in the table. And we run the Herbie regimes algorithm on the subset that is lower than this cost bound. That is, in the first iteration, we'll run it on all the candidates. And this will give us an expression. And then we repeat this by lowering the cost bound so that in the next iteration, we produce a different candidate. And we just do this until no candidate in the table is below this cost bound. So here's a more concrete example. Say we have this expression in the upper right as our input, and we've run the main loop many times, so our table has many candidates. So as we step through, we extract expressions using Herbie's regimes, and then we shrink the table, and we iteratively do this. And as you can see on the bottom left, as we map the output expression error and latency, we construct the proto-frontier of expressions. And we do this until the candidate table is empty. So that is the main changes we made to Herbie to make Furby. For the evaluation, we use 2 main benchmark suites: numerical methods for scientists and engineers, which is a standard textbook on numerical analysis with naive examples, and physically based rendering, which is an open source textbook that describes how to render photorealistic scenes. So let's go over 3 examples. The black square in the bottom right that's cut off, that is the error and cost of the input expression above. And all the red dots are the error and cost of the output expressions from Furby. And the key is Herbie will produce the one on the bottom right because all it cares about is accuracy, but it misses all these other interesting implementations, especially this one on left that only uses arithmetic operators and is still fairly accurate. Here's a second example. Once again, Herbie only produces the one on the far right. And a third example where the interesting thing here is there are these implementations that are lower in cost and lower in error than the input expression. So I made the claim in the beginning that finer interleavings of the 2 techniques create better Pareto frontiers. We use 7 treatments on the 2 benchmark suites. The 4 that are of interest are the 2 in the middle that use rewriting and tuning, precision tuning separately, and the 2 on the right that use the 2 techniques together. Of course, we have Furby, but we also have a kind of a coarser grain variant that uses precision tuning and rewriting together rather inefficiently. And this is the kind of the aggregate result on the 2 benchmarks. And what these curves answer is if you were to choose one output expression from each benchmark within the suite, and you sum the cost and sum the error, for a given cost bound, what is the minimum error you can achieve? And as you can see for both benchmark suites, the 2 treatments that interleave precision tuning and rewriting perform much better than the 2 treatments that use the techniques back to back. So that's our evaluation. Here's the rest of the team that worked on the original Arith paper, as well as their sponsors. And that's the end of my talk. Furby is currently in experimental mode within Herbie 1.5, which just released a few days ago. So please check out out the website for more information. Thanks for listening.